What if I told you the universe isn't as smooth as it seems? What if, when you zoom in far enough past planets, past atoms, even past the tiniest particles we know, space-time itself starts to look frothy? Like a bubbling, seething ocean of energy at the smallest scales imaginable. This isn't science fiction. It's one of the most mind-bending ideas in physics today: quantum foam, the hidden fabric of reality itself. Think about that for a second. The very stage of the universe, the backdrop against which everything plays out, might not be a calm, steady surface but a chaotic, fluctuating foam at the quantum level. And if that's true, it changes everything we thought we knew about space, time, and the nature of existence. For decades, scientists have been piecing together clues about what space-time is really made of. Einstein's theory of relativity paints it as a smooth, flexible sheet, a cosmic trampoline warped by stars and galaxies. But when we dive into the quantum world, things get wild. Particles pop in and out of existence, energy fluctuates unpredictably, and at the very smallest scales, space-time might not be continuous at all. It could be a frothy, turbulent sea of tiny bubbles, constantly forming and vanishing in a dance we can't even see. This is quantum foam, a theory so radical it challenges our most basic assumptions about reality. And here's the kicker: if it's real, it could hold the key to unlocking the ultimate theory of everything, bridging the gap between gravity and quantum mechanics. So why haven't you heard more about it? Because quantum foam exists in a realm so small, so fleeting, that our best instruments can't even detect it yet. But the implications are staggering. Imagine if the ground beneath your feet wasn't solid but made of invisible, shifting bubbles. That's the universe we might be living in. And today, we're going to explore 25 groundbreaking theories about quantum foam, from its role in black holes to its connection with dark energy, and even the possibility of miniature wormholes hidden in the fabric of space. This isn't just about physics, it's about peering into the deepest mysteries of existence. So buckle up, we're about to take a journey to the very edge of what we know, and maybe even beyond. Picture the smallest possible distance you can think of, 1,000,000 times smaller than an atom, tinier than anything we've ever observed. This is the Planck scale, where the rules of gravity and quantum mechanics collide in a storm of uncertainty. At this unimaginably small level, space-time itself might dissolve into a seething, chaotic froth, what physicists call quantum foam. Think of it like looking at the surface of a calm pond through a microscope. From far away, the water seems smooth and unbroken, but zoom in close enough and you'll see a turbulent dance of bubbles constantly forming and popping. That's the essence of the Planck scale foam hypothesis. Space-time isn't smooth at all but a churning, fluctuating mess at the tiniest scales. Now here's the twist: we can't see it. Not yet, anyway. The Planck length is so vanishingly small that even our most advanced particle colliders and telescopes can't probe it directly. Imagine trying to measure the ripples in a pond with a mile-long ruler. It's just not built for that level of detail. But even without direct proof, the math behind this idea is compelling. Quantum mechanics tells us that empty space isn't truly empty. Virtual particles flicker in and out of existence, borrowing energy from the universe in fleeting bursts. If that's happening everywhere all the time, then space-time itself might be built from this same erratic energy, creating a foamy structure beneath our feet. What does this mean for reality? Well, if space-time is foamy at the Planck scale, it challenges Einstein's smooth, continuous universe. Gravity and quantum mechanics, two pillars of physics that stubbornly refuse to work together, might finally find common ground in this turbulent quantum sea. Some theories even suggest that tiny wormholes could constantly form and vanish in this foam, linking distant parts of the universe in an instant like tunnels through the froth. And if we ever figure out how to detect these Planck scale fluctuations, it could revolutionize everything from black hole physics to the nature of dark energy. But for now, quantum foam remains just beyond our grasp, a ghostly whisper in the equations of theoretical physics. It's a reminder that the universe still holds mysteries far stranger than we've dared to imagine, lurking in the spaces between everything we know. If spacetime is a bubbling quantum foam at its smallest scales, what other secrets might be hiding in that chaos? One tantalizing possibility is that this frothy sea of spacetime could be threaded with microscopic wormholes, tiny tunnels that connect distant points in space and time. Think of them as shortcuts woven into the very fabric of reality, so small you could never walk through them, but significant enough to rewrite our understanding of the cosmos. This idea traces back to physicist John Wheeler, who first speculated that quantum foam might not just be random fluctuations, but a dynamic network of these minuscule wormholes. Picture a sponge where every pore is a potential gateway. On the Planck scale, these tunnels could constantly form, collapse, and reconnect in a frenzied dance. While they'd be far too tiny for anything to traverse intact, their existence could solve some of physics' biggest headaches, like how particles seem to know each other's states instantaneously across vast distances, a phenomenon Einstein famously called spooky action at a distance. Here's where it gets even wilder. Some theories suggest these wormholes might be the missing link between quantum mechanics and gravity. In Einstein's relativity, wormholes are cosmic bridges warping spacetime on enormous scales. But in the quantum realm, they could be the glue that binds particles together through hidden connections in the foam. It's as if the universe has a secret subway system operating beneath the surface of reality, with trains too small to see but essential for keeping everything running. Of course, there's a catch. Proving it. These wormholes would exist for mere fractions of a second at sizes a billionth of a proton. Even if we could detect them, they'd likely vanish before we could study them. Yet their theoretical fingerprints might still be visible. Some scientists propose that if we examine the behavior of particles or light with extreme precision, we might spot subtle anomalies, hints that spacetime isn't smooth but riddled with these fleeting tunnels. And if they're real, the implications are staggering. From explaining dark energy to unlocking faster-than-light communication, not by traveling through wormholes, but by exploiting their quantum connections, this could be the first step toward a unified theory of everything. It's a reminder that sometimes the universe's boldest secrets are hidden not in the vastness of space, but in the foam beneath our feet. Could the restless foam of spacetime hold the secret to one of the greatest mysteries in cosmology, dark energy? Scientists have long wrestled with the baffling fact that our universe isn't just expanding, but doing so at an accelerating rate. Something invisible, something relentless is pushing galaxies apart faster and faster. We call it dark energy, but its true nature remains elusive. Now, some theorists propose an astonishing connection. What if the very fabric of quantum foam is fueling this cosmic acceleration? At the heart of this idea lies a peculiar property of the quantum vacuum. Even in so-called empty space, particles flicker into existence, borrowing energy from the universe before vanishing again. These fluctuations aren't just random noise, they carry real, measurable energy. And if spacetime itself is a foamy sea at the smallest scales, these endless bubbles of creation and annihilation might be adding up to something far bigger. Picture blowing into a glass of soda. Each tiny bubble alone seems insignificant, but together they create a frothing force that could overflow the glass. Similarly, the cumulative energy of quantum foam fluctuations might be driving the universe's expansion. The math behind this is both elegant and mind-bending. Certain models suggest that at the Planck scale, the foam's chaotic behavior could produce a form of negative pressure, a sort of anti-gravity effect embedded in spacetime itself. This wouldn't just explain dark energy, it would weave it directly into the structure of reality. Imagine spacetime as a stretchy fabric, but instead of being pulled taut, it's constantly bubbling with microscopic springs that push outward. Over cosmic distances, that subtle push becomes the engine of universal expansion. But there's a problem. When physicists try to calculate how much energy quantum foam should contribute, the numbers explode to absurdly large values far beyond what we observe in dark energy. This cosmological constant problem has been a thorn in the side of theoretical physics for decades. Some researchers argue we're missing a crucial piece of the puzzle, perhaps a hidden symmetry or a yet undiscovered quantum effect that tames these runaway numbers. Others propose that the foam's fluctuations might cancel out in unexpected ways, leaving behind just the faint residue we detect as dark energy. What makes this theory so compelling is its sheer audacity. It suggests that the answer to a cosmic-scale mystery might lie in the universe's smallest, most turbulent corners, that the invisible hand shaping galaxies could be the collective sigh of spacetime itself, whispering in Planck-length bubbles. While we're still far from definitive proof, the quest to link quantum foam and dark energy represents one of the most thrilling frontiers in physics, where the unimaginably small meets the incomprehensibly vast in a dance we're only beginning to understand. Quantum foam might be hiding more than just wormholes or dark energy. It could be the universe's ultimate backup system. Imagine if every time a black hole devoured a star, it wasn't erasing information but encoding it into the very fabric of spacetime, like cosmic graffiti etched into the foam. This is the radical idea behind the quantum error-correcting code theory, where the frothy chaos at the Planck scale isn't random noise but a finely tuned mechanism keeping reality from glitching. Think of it like a computer safeguarding its data. When files get corrupted, error-correcting algorithms step in to reconstruct the missing pieces. Now stretch that idea across the cosmos. Black holes, those infamous information shredders, might not be the end of the story. Instead, as matter falls in, its quantum blueprint could get scrambled into the foam's fluctuations, a distributed storage system so robust that not even a singularity can destroy it. The foam wouldn't just remember the information, it would actively repair any inconsistencies like a self-healing cosmic hard drive. This theory tackles one of physics' biggest headaches, the black hole information paradox. If black holes truly erased information, it would violate quantum mechanics' core rule that information can't be destroyed. But if spacetime foam acts as a correction code, it would mean the universe has built-in redundancy, preserving every bit of data in a form we're only beginning to decipher. Picture dropping a book into a fire. The pages burn, but if someone scattered the ashes in a precise pattern, a future civilization could theoretically reconstruct every word. Quantum foam might be doing something eerily similar, just on a subatomic scale. The implications are staggering. If true, it would mean the universe isn't just governed by random fluctuations but by an underlying order, a hidden logic woven into spacetime itself. Some researchers even suggest this could be the missing link between gravity and quantum mechanics, where the foam's chaotic appearance masks a deeper computational structure. It's as if the cosmos runs on an operating system we're only now glimpsing through equations. Of course, proving this isn't easy. Detecting such delicate information storage would require observing effects trillions of times smaller than anything our instruments can currently measure. But the math holds tantalizing clues. Certain quantum gravity models predict that black hole radiation. The faint glow they emit might carry subtle imprints of this encoded data, like cosmic Morse code hidden in static. And if we ever crack that code, it wouldn't just solve a paradox, it would reveal that the universe is far more resilient and far more ingenious than we ever imagined. What if our entire three-dimensional universe is just a projection, a cosmic hologram flickering on the surface of spacetime itself? This isn't science fiction. It's the heart of the holographic principle, a theory so revolutionary it could rewrite our understanding of reality. And here's where quantum foam enters the picture. If spacetime is indeed a seething, chaotic froth at the smallest scales, that foam might not just be random noise. it could be the pixels of a vast cosmic hologram, encoding all the information about our universe on an invisible, lower-dimensional boundary. Think of it like a movie screen. When you watch a film, you're not seeing the actual actors, you're seeing light projected onto a flat surface that tricks your brain into perceiving depth. The holographic principle suggests something similar. The three-dimensional world we experience, stars, galaxies, even our own bodies, might be a projection of information stored on a two-dimensional surface at the universe's edge. And quantum foam, that could be the granularity of the projection, the tiny pixels that make up the image. Every fluctuation in the foam, every bubble that forms and pops, might represent a bit of data in this cosmic code. This idea emerges from a startling discovery about black holes. When matter falls into a black hole, it doesn't just vanish, the information it carries gets smeared across the event horizon, the point of no return. This led physicists like Leonard Susskind to propose that all the information inside a black hole, indeed inside any region of space, could be encoded on its boundary. Now stretch that idea to the entire universe. If a black hole's interior can be described by information on its surface, maybe our whole cosmos works the same way. Quantum foam, with its frenetic fluctuations, could be the mechanism that makes this possible, the physical manifestation of information being constantly rewritten on reality's hard drive. The implications are staggering. If the holographic principle is correct, it would mean the universe fundamentally operates like a quantum computer, with spacetime itself as its display. The foam's chaotic appearance might just be the surface-level turbulence of deeper, more orderly processes like the static on a TV screen hiding the coherent signal beneath. Some models even suggest that the foam's fluctuations aren't random but are computations, the universe processing information in real time. But how could something as intangible as information create the solid world we know? Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots spread apart, but they're still connected by the rubber's hidden structure. In the holographic universe, quantum foam might be that hidden structure, the bridge between the two-dimensional code and the three-dimensional reality we perceive. Every particle, every force could just be a different pattern in the foam's flickering dance. Of course, this raises mind-bending questions. If we're living in a hologram, what's outside the projection? Could the foam's fluctuations be glitches in the system? And if information is truly fundamental, does that mean reality is, at its core, made of something more like thought than matter? While we're far from definitive answers, the mere possibility reshapes how we see existence. The quantum foam beneath our feet might not just be the fabric of space-time. It could be the brushstrokes of a universe painting itself into being. Even the emptiest void in the universe is far from empty. What we call empty space is actually a seething, bubbling quantum vacuum, where particles and antiparticles constantly flicker into existence for unimaginably brief moments before annihilating each other. These aren't just mathematical quirks. They're real fluctuations that have been measured in lab experiments like the Casimir effect, where two metal plates placed incredibly close together feel a faint push from these virtual particles popping in and out of being outside them. Now imagine that same frenetic activity happening everywhere all the time, at scales so small they make atoms look like giant boulders in comparison. This is where the quantum foam hypothesis gets truly fascinating, because what if these vacuum fluctuations aren't just happening in spacetime, but are the very substance of spacetime itself? At the Planck scale, where distances become almost meaningless in their tininess, these particle-antiparticle pairs might not simply appear against the backdrop of space, they could be weaving the fabric of space. Picture a stormy ocean where each crashing wave is made of countless droplets. From far away, it looks like a continuous surface, but up close, it's nothing but chaotic motion. Similarly, the smooth spacetime we experience could be an illusion created by the frenzied dance of these quantum fluctuations. Every bubble in the foam might represent a momentary pair of virtual particles warping the fabric of reality itself before vanishing back into the quantum background. This leads to an astonishing possibility. Gravity itself could emerge from this churning quantum sea. Einstein showed us that massive objects bend spacetime like a bowling ball on a trampoline. But what if that curvature is actually the collective effect of countless quantum fluctuations being subtly reshaped by matter? It's like dropping a stone into that stormy ocean. The individual droplets still behave randomly, but overall, their motion bends around the stone's presence. Some theoretical models suggest this could be the missing link between quantum mechanics and general relativity, where the foam's chaotic behavior at microscopic scales averages out to the smooth gravitational curves we observe in the cosmos. But here's where things get even stranger. These vacuum fluctuations don't just warp space, they might also be twisting time. Quantum foam could mean that at the smallest scales, time itself stutters and jumps rather than flowing smoothly, like a film reel with missing frames. Experiments with ultra-precise atomic clocks have already shown that time ticks slightly differently at different heights, a confirmation of Einstein's relativity. But some physicists speculate that if we could measure time intervals short enough, we'd find it behaves more like a series of quantum leaps than a river. The foam's fluctuations might momentarily create tiny time reversals or discontinuities, though these would average out so completely in our macroscopic world that we'd never notice. The most mind-bending implication: if spacetime is truly built from these quantum fluctuations, then the distinction between something and nothing starts to blur. The vacuum isn't just a stage for particles to perform on, it's an active participant, constantly birthing and destroying potential realities. This challenges our deepest notions of existence, suggesting that what we perceive as stable and permanent might just be the most probable outcome of countless quantum probabilities playing out beneath the surface. It's as if the universe is a restless artist, endlessly sketching possibilities in spacetime foam, with only the most persistent drafts surviving long enough for us to call them real. While we can't yet peer directly into this quantum froth, there are tantalizing hints in the behavior of high-energy cosmic rays. Some physicists suggest that if spacetime has this foamy structure, ultra-high-energy particles traveling across the universe should interact with it in subtle ways, perhaps slowing down very slightly or scattering in patterns we could detect. It's like throwing a handful of sand into the air to study the wind. We can't see the breeze itself, but we can learn from how the sand moves. Future experiments with more sensitive detectors might finally catch these whispers from the quantum depths, revealing whether the vacuum's restless energy is truly the threads from which reality is woven. What makes this theory so compelling is how radically it reimagines the stage of existence. We're used to thinking of space as a passive container and time as an indifferent flow, but quantum foam suggests they're alive with possibility, a dynamic, ever-changing medium where even the vacuum brims with potential. It's a reminder that in the quantum realm, nothing ever truly sits still, and the solid ground beneath our feet might be the most astonishing illusion of all. While Einstein's relativity paints spacetime as a smooth, unbroken fabric, loop quantum gravity offers a radically different vision, one where the universe is stitched together from discrete, indivisible threads. Imagine zooming in on the weave of a tapestry until you see the individual fibers. At this unimaginably small scale, loop quantum gravity suggests spacetime isn't continuous at all but quantized, built from tiny, woven loops of gravity itself. These loops intertwine to form a dynamic structure called spin foam, a bubbling, evolving network that replaces the classical notion of smooth spacetime with something far more intricate. This spin foam isn't just a metaphor, it's a mathematical reality where each loop carries a quantized packet of spacetime like pixels on a screen. Where general relativity sees a flowing river, loop quantum gravity sees individual droplets, tiny grains of space and time that can't be divided further. These grains don't just sit passively, they interact, merge, and split in a frothy dance, creating what we perceive as quantum foam. The foam's chaotic appearance arises from this constant rewiring of spacetime's fundamental structure, like a cosmic game of cat's cradle played with gravitational threads. What's remarkable is how this framework tackles one of physics' greatest challenges, uniting gravity with quantum mechanics. In loop quantum gravity, the foam's fluctuations aren't random noise but the result of precise, quantized interactions between spacetime's building blocks. Picture a grid of interconnected springs where each connection represents a possible state of spacetime. As these springs stretch and shift, they generate the foam-like behavior we associate with the Planck scale. This means gravity itself could emerge from the collective behavior of these loops, bridging the gap between the quantum world and the cosmic scale. The implications are profound. If spacetime is truly granular, then concepts like before and after might break down at the smallest scales. Time itself could become a series of quantum jumps rather than a smooth flow, like frames in a film strip where the intervals between frames are the foam's fleeting rearrangements. Some models even suggest that black hole singularities might vanish in this framework, replaced by a dense web of spin foam where gravity's pull reaches a natural limit instead of spiraling into infinity. Yet the theory isn't without its puzzles. While spin foam beautifully quantizes space, it struggles to explain how this granularity smooths out into the continuous spacetime we observe. It's like trying to reconcile the jagged edges of a mosaic with the illusion of a seamless painting when viewed from afar, and without experimental proof, no instrument can yet probe the Planck scale. The idea remains a tantalizing hypothesis. But if future technology ever catches up to the math, we might discover that the universe isn't just foamy but woven, its deepest truths tied in loops too small to see but too fundamental to ignore. Einstein once dismissed quantum entanglement as spooky action at a distance, a phenomenon so bizarre it seemed to defy the very notion of space. But what if the answer to this mystery has been hiding in the quantum foam all along? Some physicists now speculate that the strange, instantaneous connections between entangled particles might emerge from deeper links woven into spacetime's frothy foundation. Imagine two corks floating on a turbulent sea. From the surface, they might appear to move independently until you realize they're connected by invisible currents beneath the waves. Quantum foam could be those hidden currents with entangled particles acting like corks bobbing on a shared network of Planck-scale turbulence. This idea flips traditional thinking on its head. Instead of entanglement being a weird quirk of particles, it might be a fundamental feature of spacetime itself. At the foam's chaotic level, tiny wormholes or geometric threads could tether distant points together, creating correlations that persist no matter how far apart particles travel. It's like shaking a spiderweb. Pluck one thread, and the vibration echoes instantly across the entire structure. In this view, what we call non-locality isn't a violation of cosmic speed limits, but a revelation that seemingly separate points in space were never truly disconnected to begin with. The math behind this is as elegant as it is radical. Certain quantum gravity models suggest that entangled particles might share microscopic bridges in the foam shortcuts through spacetime's underlying structure. These bridges wouldn't transmit information faster than light. They'd simply bypass the idea of distance altogether. Picture two rooms connected by a secret hallway. Walking through the main corridors would take time, but the hidden passage makes the journey instantaneous. Similarly, quantum foam could be riddled with these Planck-scale hallways, making entanglement less like teleportation and more like taking the universe's backroads. But here's where it gets even wilder. If entanglement stems from spacetime's foamy architecture, it could mean the universe is far more interconnected than we ever imagined. Every particle, every atom might be subtly linked through this submerged quantum web. Some theories go further, proposing that what we perceive as empty space is actually a dense tapestry of these entanglements, a cosmic neural network where separate objects are just in points of the same tangled threads. This wouldn't just explain spooky action, it could redefine our understanding of what it means to be a part in the first place. Of course, testing these ideas isn't easy. The foam's structures would exist at scales a billion times smaller than anything we can probe, but indirect clues might lie in high-precision entanglement experiments. If spacetime's granularity subtly alters how entangled particles behave at extreme distances or energies, future quantum sensors could catch these whispers from the foam. It's the universe's ultimate sleight of hand, hiding its deepest connections in plain sight, waiting for us to recognize the threads stitching reality together. Time travel has long been the stuff of science fiction, but what if the key to bending time isn't found in some massive machine, but in the frothy quantum foam beneath our feet? The wildest theories suggest that spacetime's chaotic microscopic structure might hold the secret to looping back on itself, creating what physicists call closed time-like curves, paths through the universe that twist back to their own beginnings. Imagine stirring a cup of coffee until a tiny whirlpool forms where the liquid folds back into itself. Now picture that same swirling motion, but woven into the very fabric of reality at the Planck scale. That's the tantalizing possibility hiding in quantum foam. At first glance, the idea seems impossible. Einstein's relativity allows for time warps near massive objects like black holes, but quantum foam takes this further, proposing that spacetime's turbulence at microscopic scales could naturally spawn fleeting tunnels where time loops back. Think of it like walking on a Möbius strip. Normally, you'd move forward in a straight line, but if spacetime is twisted just right at the quantum level, your path might unexpectedly circle back to where you started. These loops wouldn't resemble Hollywood time machines. They'd be more like cracks in reality's foundation, so unstable and tiny that anything trying to traverse them would be shredded by quantum fluctuations. The math gets even stranger. Some models suggest that if you could manipulate the foam's structure, perhaps by concentrating unimaginable energy or exploiting exotic matter, you might stabilize one of these loops long enough to create a usable time circuit. It's like trying to hold a soap bubble steady between your hands. The harder you grip, the faster it pops. But if you could somehow balance the forces perfectly, even for an instant, the bubble might last just long enough to send information or, theoretically, a particle back to an earlier moment in its own timeline. The catch: the energy required would dwarf anything our civilization could produce, and the side effects could be catastrophic. Here's where things get paradoxical. If time travel were possible through quantum foam, why haven't we met visitors from the future? One unsettling answer lies in the foam's chaotic nature. Any attempt to traverse a closed time-like curve might trigger a feedback loop of quantum interference, effectively erasing the time traveler from existence. Picture throwing a stone into a pond where ripples collide so violently they cancel each other out. The foam's turbulence could act like those ripples, self-correcting to prevent paradoxes by deleting any inconsistencies. This wouldn't just protect causality, it would mean the universe has built-in safeguards against meddling with time. Yet the most compelling evidence for foam-based time loops might already exist in black holes. Near a singularity, gravity warps spacetime so intensely that some theories predict the foam's structure could knot into permanent closed time-like curves. If true, falling into a black hole might not mean annihilation, but an endless trip through your own past. Of course, you'd never escape to tell the tale, but the mere possibility reshapes how we view time's arrow. Perhaps the foam doesn't just allow time travel. Perhaps it's constantly spawning and dissolving these loops like cosmic eddies, invisible to us only because we're too large to notice. The sobering truth is that we're still light years from proving or disproving these ideas, but the mere fact that respected physicists take them seriously speaks volumes about quantum foam's radical potential. It's a reminder that time may not be the steady river we perceive, but a churning rapid full of hidden whirlpools just beneath the surface. Black holes have long been cosmic paradoxes, objects so dense they trap light itself, yet seemingly erase all information that falls in. But what if the solution to this puzzle lies in the chaotic quantum foam churning at their edges? The firewall hypothesis suggests something shocking. The smooth event horizon we've imagined for decades might actually be a seething Planck-scale inferno, a wall of fire made from spacetime's own turbulent foam. Picture approaching a waterfall. From far away, the water seems to flow smoothly over the edge, but get too close and you discover a violent, frothing chaos where the current tears itself apart. That's what might await anything crossing a black hole's threshold. Not a gentle slide into darkness, but an annihilation in the foam's fury. This radical idea emerged as a way to salvage quantum mechanics from the black hole information paradox. If information can't be destroyed, a cornerstone of quantum theory, then how does it escape when matter vanishes into a singularity? The firewall proposes an answer. The quantum foam at the event horizon scrambles and radiates that information back out as Hawking radiation, but at a terrible cost. Anything falling in wouldn't just stretch apart from tidal forces. It'd be vaporized instantaneously by the foam's extreme energy fluctuations. Think of throwing a book into a shredder where the blades are made of spacetime itself. The words might technically survive, but only as confetti scattered across the universe. Critics argue this turns black holes into cosmic absurdities. Einstein's relativity insists that crossing an event horizon should feel uneventful. An observer falling in wouldn't notice anything special until gravity's pull became unbearable. But if firewalls are real, relativity and quantum mechanics clash violently right at the horizon. It's like two architects designing opposite halves of a bridge that can't possibly meet. Supporters counter that maybe smooth horizons were always an illusion, that the foam's turbulence is the universe's way of enforcing quantum rules, even if it means rewriting Einstein's playbook. The debate hinges on how quantum foam behaves under extreme gravity. Some models suggest the foam's fluctuations become so frenzied near a black hole that they crystallize into a structured chaos, a lattice of Planck-scale fireworks encoding information in their patterns. Others propose the firewall isn't a permanent feature but emerges dynamically as the black hole ages, like crust forming on lava. There's even a stranger possibility that the foam's activity creates multiple copies of infalling matter. One burned at the firewall, another continuing inward unscathed, as if reality itself can't decide between quantum and relativistic demand. If firewalls exist, they'd rewrite not just black hole physics but our understanding of spacetime's resilience. A seething horizon would mean the universe has built-in censorship, preventing any observer from witnessing contradictions between quantum and classical worlds. It's as if the cosmos draws a curtain at the edge of black holes, shielding us from seeing how the magic trick really works. Future gravitational wave detectors might hunt for firewall signatures in merging black holes, perhaps faint, high-energy glitches in the signal as horizons collide. Until then, the firewall remains a thrilling, contentious clue that the answers we seek might lie in the foam's untamed storm. Ever wondered if empty space could push? In 1948, physicist Casimir predicted something astonishing: that two metal plates placed incredibly close together in a vacuum would inexplicably be drawn toward each other, as if space itself was pressing them together. When scientists finally measured this tiny force decades later, they weren't just confirming a quirky prediction, they might have been glimpsing the restless churn of quantum foam in action. Here's how it works. Even in a perfect vacuum, quantum mechanics tells us that virtual particles constantly flicker into existence, borrowing energy from the universe before vanishing again. These fleeting fluctuations create a sort of quantum pressure all around us, but when two plates are brought extremely close, within a few millionths of a meter, something strange happens. Only certain wavelengths of these virtual particles can fit between the plates, while outside them, all wavelengths roam freely. This imbalance creates a pressure differential, literally pushing the plates together with a measurable force. It's like placing two boats in a stormy sea where the waves between them are calmer. The more chaotic waves outside will naturally push them inward. Now, here's where quantum foam enters the picture. If spacetime itself is a turbulent froth at the Planck scale, then the Casimir effect might be our first tangible clue to its existence. The particles flickering in and out of the vacuum aren't just happening in space. They could be manifestations of spacetime's underlying foam, like bubbles rising to the surface of a boiling pot. When the plates suppress some of those fluctuations, they're effectively smoothing out a tiny patch of the foam, revealing the raw, restless energy that's always there beneath the illusion of stillness. Some physicists take this even further. The Casimir force's precise strength aligns suspiciously well with calculations of vacuum energy density, the same energy that quantum foam theories suggest permeates all of space. It's as if the experiment taps into the foam's background hum, letting us hear the universe's hidden static. And if that's true, then every time we measure the Casimir effect, we're not just observing empty space, we're detecting the tremors of spacetime's deepest structure. Yet mysteries remain. The energy densities implied by the Casimir effect are enormous compared to what we observe in the larger cosmos, raising questions about how the foam's frenzy averages out to the relatively calm universe we inhabit. Some theories propose that the foam's fluctuations might cancel out at larger scales, like waves in the ocean that look chaotic up close but smooth into a steady tide from afar. Others suggest we're missing a crucial piece of the puzzle, perhaps undiscovered symmetries or undiscovered physics that reconcile the foam's microscopic violence with the universe's macroscopic serenity. What makes the Casimir effect so compelling is that it's not just theoretical, it's a real, measurable phenomenon that stubbornly points toward the foam's existence. Future experiments with even more precise measurements or exotic materials might reveal new layers of this quantum whisper, helping us decode whether the force between those plates is truly the fingerprint of spacetime's hidden turbulence. For now, it stands as one of our most tantalizing hints that the vacuum isn't empty at all but alive with the foam's endless dance. The universe burst into existence not with a bang, but a bubble, countless bubbles actually. One of the most compelling theories about quantum foam suggests it didn't just shape spacetime. It might have kickstarted the entire cosmic expansion we see today. Picture the early universe as a superheated, seething quantum soup, where spacetime wasn't just frothy but violently unstable. In those first, incomprehensibly short moments, some physicists believed the foam's fluctuations didn't just ripple. They erupted, triggering a runaway expansion called cosmic inflation that stretched the infant cosmos from smaller than an atom to nearly its current size in less than a blink. What's startling about this idea is how neatly it solves two of cosmology's biggest puzzles. First, why is the universe so uniform? Distant regions of space look eerily similar, even though they've never had time to exchange information. Inflation explains this by proposing everything was once close enough to equalize before being flung apart. But here's the twist: inflation itself might have been powered by quantum foam's turbulent energy. Imagine blowing up a balloon covered in tiny pores. If you suddenly heated it, the pores would boil over with steam, forcing the balloon to expand rapidly. Similarly, the early universe's foam could have unleashed pent-up vacuum energy, creating the pressure needed for exponential growth. The second puzzle is the universe's bizarre flatness. The way space-time appears perfectly balanced between collapsing and flying apart. Inflation stretches any initial curvature until it looks flat, like zooming in on a wrinkle until it vanishes. But the real magic lies in how quantum foam could have seeded this process. Some models suggest that random fluctuations in the foam structure tiny differences in energy from one Planck-sized patch to another, got stretched to cosmic scales during inflation, eventually becoming the galaxies and voids we see today. It's as if the foam's microscopic chaos wrote the blueprint for the entire large-scale universe, with every star and galaxy tracing back to a quantum hiccup in the first trillionth of a second. Not everyone agrees, of course. Some theorists argue that while foam might have played a role, inflation was likely driven by a different quantum field, the inflaton. Others propose even wilder ideas, like the universe being born from a collision between foam-like membranes in higher dimensions. But the foam-inflation connection holds a unique appeal because it ties together the very smallest and largest scales of physics without inventing new particles or forces. The same frothy turbulence that makes virtual particles flicker at the Planck scale might have once been powerful enough to stretch spacetime itself. The most tantalizing evidence for this theory, it's written in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light match predictions of quantum fluctuations stretched by inflation. It's like finding the faded fingerprints of the universe's quantum origin still visible in the sky. Future gravitational wave detectors might hunt for even subtler traces, ripples in spacetime that could carry echoes of the foam's primordial fury. If they find them, it would mean our vast, smooth cosmos wasn't just born from chaos, it's the magnified reflection of spacetime's tiniest tremors frozen in time. What if the quantum foam beneath reality isn't just physics? It's code. The simulation hypothesis, once relegated to philosophy and science fiction, gains eerie plausibility when you consider spacetime's pixelated nature at the Planck scale. Think of the universe as an ultra-high-resolution video game where the graphics appear seamless until you zoom in close enough to see individual pixels. Quantum foam could be those pixels, the fundamental bits of a cosmic computer rendering reality in real time. This isn't just a metaphor. If spacetime truly has a discrete, grainy structure at its smallest scales, it aligns suspiciously well with how simulations operate. Every virtual world, from the simplest computer game to the most advanced AI training environment, relies on finite computational resources. Smooth curves and continuous motion are illusions created by tiny, indivisible steps. The foam's chaotic fluctuations might be the universe's version of computational noise, the background processing required to maintain the simulation's fidelity. Even the speed of light could be seen as the processor's clock speed, setting an upper limit for how quickly information propagates across the cosmic program. Supporters of this view point to strange mathematical coincidences. The Planck length, the smallest meaningful distance in quantum foam, is roughly where quantum gravity effects dominate, making it nature's equivalent of a pixel size. Just as a screen can't display details smaller than 1 pixel, reality might render only down to Planck scale resolution. Even more intriguing, some calculations suggest the universe's total information content fits within bounds predicted by theoretical computer science, as if spacetime were an optimized data structure. But the simulation argument goes deeper than neat analogies. Quantum foam's unpredictable fluctuations could be glitches, artifacts of limited computational precision. Ever notice how video games sometimes show texture flickering or physics errors when pushed to their limits? The bizarre behavior of particles at quantum scales, where they exist in multiple states until observed, might reflect similar resource-saving optimizations. In a simulated universe, rendering every particle's exact state at all times would be computationally wasteful. Instead, the system might only calculate precise properties when someone's looking, much like a game engine only renders graphics in the player's field of view. Critics counter that invoking a simulator is unnecessary when physics already explains quantum behavior. Yet the simulation hypothesis offers solutions to enduring mysteries. Why do quantum particles instantly know each other's states across vast distances? Maybe because they're not separate entities but data points linked in the simulator's memory. Why does the vacuum have non-zero energy? It could be the background processes keeping the simulation running. Even the holographic principle fits neatly. A 3D universe encoded on a 2D boundary resembles how computer graphics often use projection techniques to save processing power. The most unsettling implication isn't that we're in a simulation, but that quantum foam might be our only window into its underlying rules. Like characters in a game discovering their world has frame rate limits, Planck scale phenomena from the uncertainty principle to vacuum fluctuations could be glimpses of the universe's source code. Future experiments probing spacetime's granularity might reveal patterns resembling error correction algorithms or computational architectures. Until then, the foam remains both a scientific frontier and the ultimate philosophical riddle. Are we decoding nature's laws or someone else's programming? Could consciousness itself be woven into the quantum foam of spacetime? It sounds like the plot of a sci-fi novel, but some physicists and philosophers are seriously considering whether the mind's deepest mysteries might be entangled with the universe's smallest structures. At the heart of this radical idea lies a simple question. If reality is fundamentally made of fluctuating, probabilistic foam at its core, could our subjective experience, our thoughts, perceptions, even free will, somehow emerge from or interact with that chaos? Take the Orch-or theory proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum computations happening in microtubules, tiny protein structures inside brain cells. But here's where it gets wild. These quantum processes might not stay confined to the brain. Instead, they could connect to the broader quantum foam, with each conscious moment being a collapse of spacetime's inherent uncertainty into something definite. Picture throwing a stone into a foamy ocean. The ripples don't just stay in one place, they spread. Similarly, our thoughts might not just be neural firings, but ripples in the fabric of reality itself. Critics dismiss this as speculative, pointing out the brain's warm, wet environment should destroy fragile quantum states almost instantly. Yet supporters counter that quantum biology, like photosynthesis relying on quantum effects in plants, hints nature might have found ways to harness quantum phenomena even in messy biological systems. And if quantum foam permeates everything, perhaps the brain evolved to tap into it, like a radio tuning into hidden frequencies. Even stranger is the notion that consciousness might not just arise from the foam but influence it. Some interpretations of quantum mechanics, like von Neumann-Wigner consciousness causes collapse, suggest observation literally shapes reality. In this view, the foam's probabilistic froth only settles into concrete events when consciousness interacts with it. Imagine blowing on a dandelion puff. Your breath determines where the seeds land. If consciousness works similarly on quantum foam, our attention could be the force that crystallizes possibilities into actualities. Of course, this raises profound questions. If consciousness interacts with foam, does that mean spacetime itself is somehow aware? Panpsychism, the idea that consciousness is a fundamental property of matter, gains traction here, proposing that even elementary particles might have rudimentary experience. A quark wouldn't think, but perhaps it holds some whisper of sensation, with complex consciousness emerging as these fragments combine. It's like saying every drop in the ocean carries a trace of wetness, but only the whole ocean has waves. The most tantalizing implication: if consciousness and quantum foam are linked, altering one might change the other. Meditative states or psychedelic experiences where perception of time and space distorts could be glimpses into the foam's mutable nature. Near-death accounts of timelessness might reflect the brain's quantum processes unraveling into spacetime's deeper structure. Even déjà vu could be a glitch, a momentary misfire where conscious observation fails to fully collapse the foam's probabilities. While mainstream science remains skeptical, these ideas force us to confront how little we understand about either consciousness or quantum gravity. maybe the foam isn't just the scaffolding of space and time, but also the substrate of mind, a hidden layer where reality and perception intertwine. Until we can probe Planck-scale physics or decode the brain's quantum secrets, this remains the ultimate frontier, not just mapping the universe's fabric, but asking whether it's aware we're here. Supersymmetry isn't just another elegant theory. It might be the missing key to unlocking quantum foam's secrets. This grand idea in particle physics proposes that every known particle has a hidden, supercharged twin. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. If these supersymmetric particles exist, they wouldn't just fill gaps in our equations. They could be the very particles capable of interacting directly with the frothy chaos of spacetime itself. Imagine quantum foam as a turbulent ocean and ordinary particles as boats gliding atop the waves. They feel the motion but never truly plunge into the depths. Supersymmetric particles, though, might be like submarines built to navigate the foam's hidden currents. Some models suggest these exotic twins could carry unique quantum properties that couple them to spacetime's fluctuations in ways normal matter can't. It's the difference between skimming a stone across water and dropping a weighted net. One barely disturbs the surface, while the other drags up whatever lies beneath. Why does this matter? Because right now, quantum foam is a ghost in the equations, real enough to shape theories, but too subtle to detect. Supersymmetry offers a backdoor. If these superpartners are out there, they might leave fingerprints in high-energy collisions or rare particle decays, revealing how they interact with the foam's structure. Think of it like searching for invisible ink. Under normal light, the page looks blank, but shine the right wavelength, say, the energy scales of a futuristic collider, and hidden patterns emerge. The stakes couldn't be higher. Supersymmetric particles could solve two cosmic mysteries at once: dark matter and quantum gravity. The lightest superpartner, often called the neutralino, is a prime dark matter candidate, an invisible particle that barely interacts with ordinary matter. But what if its elusiveness isn't just a quirk of weak interactions? What if it's constantly slipping in and out of the foam, tethered to spacetime's fabric in ways we've never imagined? Experiments are already hunting for clues. When the Large Hadron Collider smashes protons together at near light speed, physicists sift through the debris for anomalies, energy that vanishes without a trace, or particles that defy known laws. These could be hints of supersymmetric particles decaying into quantum foam's hidden dimensions. It's like listening for echoes in a cave. Even if you can't see the walls, the reverberations tell you something's there. Yet supersymmetry walks a tightrope between hope and frustration. Decades of searches haven't turned up definitive proof, leading some to wonder if the theory needs revision, or if nature has a stranger surprise in store. But here's the twist: even if superparticles aren't exactly as predicted, their underlying principle might still hold. Modified versions, like split supersymmetry or stealth models, could preserve the core idea while dodging current experimental limits. The dream isn't dead, it's evolving. And if one day we catch a glimpse of these shadowy particles, it won't just confirm a theory, it'll open a portal to spacetime's hidden layer. Suddenly, quantum foam wouldn't be an abstract notion, but a dynamic medium we could probe through its interactions with supersymmetric matter. The universe's smallest scale might finally meet its most elusive particles, and in that collision, we'd uncover truths far beyond what either could reveal alone. Einstein's equations predict that at the heart of every black hole lies a singularity, a point of infinite density where spacetime curves to a mathematical breaking point. The Big Bang Theory tells a similar story. The universe began as an infinitely hot, infinitely dense speck. But infinities in physics are usually nature's way of saying we're missing something. Enter quantum foam, the universe's ultimate problem solver. What if singularities aren't truly infinite at all, but dissolve into a swirling, finite froth when you peer close enough? Picture a river cascading toward a waterfall. From a distance, the water seems to plunge into an endless abyss. but get close and you'll see churning rapids breaking the fall into chaotic, manageable steps. Quantum foam could be doing the same for singularities. At the Planck scale, spacetime's granularity might prevent infinite collapse by replacing mathematical singularities with dynamic foam-like structures. Instead of a single, infinitely dense point, a black hole's core could be a seething network of quantum loops or bubbles, a place where gravity's grip hits a natural limit set by the foam's architecture. It's like zooming in on a pixelated image. What looked like a smooth curve from afar reveals its blocky, finite nature up close. This idea flips black hole physics on its head. Rather than a destructive end point, the singularity becomes a transition zone where matter and energy are reprocessed by the foam's turbulence. Some loop quantum gravity models even suggest black holes could transform into white holes in this quantum foam, rebounding collapsed matter back out into the universe like a cosmic trampoline. Imagine a star's implosion not as a one-way trip to oblivion, but as a metamorphosis, its mass churned into foam like space-time structures before potentially re-emerging elsewhere. The same principle might apply to the Big Bang. Instead of an unknowable singularity, the universe's birth could have been a big bounce, where a previous cosmos contracted to a foam-dense state before quantum repulsion triggered expansion anew. Critics argue this just replaces one mystery with another. If singularities become foam, what governs the foam's behavior at such extremes? Yet the math holds tantalizing possibilities. In some theories, the foam's fluctuations generate enough intrinsic pressure to halt infinite collapse, like a microscopic safety net woven into spacetime itself. Others propose that black hole singularities are computational limits, not physical ones our equations break down because we're trying to describe foam with smooth geometry, like using a weather map to model every raindrop in a hurricane. The most radical implication: if singularities are illusions, we might need to rewrite cosmic history. The Big Bang wouldn't be the absolute beginning but a phase in an endless cycle of foam-driven transformations. Black holes wouldn't be tombs but gates, their interiors roiling with Planck-scale activity we're only beginning to decode. Future gravitational wave observatories could hunt for echoes of these foam-rescued singularities, subtle ripples in spacetime that carry fingerprints of quantum structure where infinity once ruled. Until then, the foam offers more than answers. It redefines the questions, turning cosmic dead ends into doorways we've yet to open. String theory paints a picture of reality far stranger than our everyday experience. A universe with not just 3 spatial dimensions, but hidden extra dimensions curled up so tightly we've never noticed them. Now imagine quantum foam, that seething Planck-scale turbulence, threading through this multidimensional landscape. What happens to spacetime's chaotic foundation when it has more directions to froth in? The answer could rewrite our understanding of everything from gravity to the birth of universes. In our familiar 3-dimensional world, quantum foam's fluctuations are like bubbles trapped in a glass, rising and popping within set boundaries. But add extra dimensions, and suddenly that foam has room to expand into geometries we can barely visualize. Some string theory models suggest these hidden dimensions might act like microscopic pressure valves, allowing the foam's energy to dissipate in ways that tame its chaotic extremes. Picture shaking a soda bottle in a small room. The spray goes everywhere, but in a vast warehouse, that same fizz disperses almost unnoticed. Similarly, foam spreading into extra dimensions could explain why spacetime appears relatively smooth at our scale despite its underlying turbulence. This dimensional escape route might solve one of physics' biggest headaches: why gravity is so weak compared to other forces. While electromagnetism can pin a magnet to your fridge against Earth's entire gravitational pull, gravity itself might seem feeble because it's partly leaking into these extra dimensions. Quantum foam could be the medium through which that leakage happens, with gravitational fluctuations spreading into unseen geometries like echoes in a maze. It's as if our universe sits on the surface of a pond, while gravity's ripples extend deeper into the water, dimensions we can't see but whose presence softens gravity's grasp on our cosmic layer. But extra dimensions don't just dilute quantum foam, they might reshape its very nature. Certain brain world scenarios propose our universe is a three-dimensional membrane floating in a higher dimensional space. In this view, foam's fluctuations could create temporary bridges between brains, like bubbles merging in a glass of champagne. These fleeting connections might explain sudden energy transfers or even spontaneous particle creation events that would seem miraculous in our limited dimensional perspective. Some theorists speculate that high-energy cosmic rays, which arrive with unexplained energies, could be the fallout of foam-driven collisions between our brain and others. The most mind-bending possibility, extra dimensions might turn quantum foam into a cosmic recycler. If foam fluctuations in higher dimensions can spawn entire baby universes, a concept called bubble nucleation, our cosmos might be one such bubble in an endless froth of multiverses. Each universe could have different physical constants depending on how its parent foam stabilized, like soap bubbles varying in size and stability. This would mean the fundamental laws we observe aren't universal truths but local accidents, frozen into place when our pocket of quantum foam cooled. Detecting these extra-dimensional signatures isn't impossible. Particle colliders might spot missing energy where gravity carries it off into hidden dimensions. Precision measurements of gravity at microscopic scales could reveal deviations from Newton's familiar inverse square law, a telltale sign of forces bleeding into extra geometries. Even the cosmic microwave background might hold clues, its subtle patterns encoding echoes of higher dimensional foam from the universe's first moments. While extra dimensions remain speculative, their potential marriage with quantum foam offers something rare in physics. A bridge between the infinitesimally small and the inconceivably vast. It suggests that spacetime's turbulence isn't just background noise. It could be the restless stirring of realities beyond our own, bubbling just beneath the surface of perception. Whether these dimensions exist or not, their theoretical interplay with foam reminds us that the universe's deepest secrets might not just be hidden in plain sight, but in directions we've yet to imagine. What if the very act of accelerating through empty space could make particles appear out of nowhere? That's the bizarre prediction of the unravel effect, a phenomenon where an observer speeding through a vacuum would perceive a warm glow of particles, while someone standing still sees nothing but darkness. At first glance, this sounds like a thought experiment gone wild, but it might hold the key to detecting quantum foam's hidden thermal signature. The unravel effect hinges on a startling idea: reality depends on your state of motion. Just as Einstein showed that time and space are relative, quantum field theory suggests particles themselves are observer-dependent. When you accelerate through space-time, you're effectively plowing through quantum fields, stirring them into a frenzy that manifests as particles. Think of a boat speeding across a still lake. The faster it goes, the more turbulent the wake becomes. For an accelerating observer, that wake isn't water but particles emerging from the quantum vacuum, with their temperature rising as acceleration increases. Now here's where quantum foam enters the picture. If spacetime is a turbulent froth at the Planck scale, the unravel effect's particles shouldn't just appear randomly, they should carry subtle imprints of the foam structure. Just as steam rising from boiling water reveals hints about the bubbles beneath, these acceleration-induced particles might encode information about spacetime's underlying chaos. Some models suggest that the unravel radiation spectrum, the precise distribution of particle energies, could deviate slightly from predictions if quantum foam's fluctuations are warping the vacuum's behavior. It's like listening to an orchestra where one instrument is slightly out of tune. The discord might point to hidden physics. The most tantalizing possibility is that the unravel effect could reveal quantum foam's temperature. Just as black holes emit Hawking radiation with a characteristic thermal signature, spacetime's foam might leave its own heat imprint on particles created by acceleration. This wouldn't be a temperature you could measure with a thermometer. It'd be a statistical fingerprint in the particle energies, a whisper of Planck-scale thermodynamics. Imagine running your hand over a rough surface. Even if you can't see the texture, you feel its grain. Similarly, the unravel effect might let us feel the foam's thermal texture through particle detections. But there's a catch. Observing this effect directly requires accelerations so extreme they're practically unattainable. To see even a faint unravel glow equivalent to room temperature, you'd need to accelerate at a quadrillion times Earth's gravity. Current particle accelerators fall laughably short, and even the intense gravity near black holes might not suffice. Yet ingenious workarounds exist. Some physicists propose simulating the unravel effect in analog systems, like supercooled atoms or vibrating crystals, where analogous particle creation can occur under lab-friendly conditions. Others look for indirect signatures, perhaps subtle anomalies in high-energy particle collisions where virtual unravel-like effects flicker into existence. The deeper implication: if the unravel effect connects to quantum foam's thermodynamics, it could mean that spacetime itself has a fundamental temperature, a remnant of its turbulent origins. Just as the cosmic microwave background preserves the heat of the Big Bang, the foam's thermal properties might echo the universe's fiery birth. Future experiments, from next-gen accelerators to quantum simulators, might one day tease out these clues, turning a mind-bending thought experiment into a window onto spacetime's hidden depths. Until then, the unravel effect stands as a tantalizing hint that the universe's coldest vacuum might still carry the warmth of its quantum foundations. Einstein's theory of general relativity describes gravity as the smooth curvature of spacetime, a cosmic stage where planets and stars dance to the rhythm of geometry. Meanwhile, quantum mechanics paints a wildly different picture, a probabilistic, particle-driven world where uncertainty reigns and tiny packets of energy flicker unpredictably. These two theories work flawlessly in their own domains, but when they collide, the math explodes into nonsense. Enter quantum foam, the potential peacemaker in this century-old feud. What if spacetime's chaotic, frothy nature at the Planck scale isn't just background noise but the missing link that finally connects these estranged giants of physics? Imagine trying to stitch together two fabrics, one smooth silk, the other a coarse, stretchy knit. On their own, each behaves predictably, but when forced to merge, they pucker and tear. Quantum foam could be the flexible thread that bridges them. At macroscopic scales, relativity's smooth spacetime emerges from the foam's turbulent behavior like waves rising from choppy seas, an average of countless microscopic fluctuations. Zoom in, and those same fluctuations reveal quantum mechanics' hallmark unpredictability, with particles popping in and out of existence like bubbles in a boiling pot. The foam doesn't erase the differences between the theories. It provides a shared language where both can coexist. One compelling approach comes from loop quantum gravity, where spacetime isn't continuous but woven from tiny, indivisible loops. These loops tangle into a dynamic spin foam, a structure that blends quantum discreteness with relativity's geometric elegance. Picture a sprawling mesh of interconnected springs. From far away, it looks like a smooth surface, but up close, you see the individual coils stretching and compressing. Gravity, in this view, isn't a fundamental force but an emergent property of the foam's ever-shifting architecture. When a star warps spacetime, it's not bending a featureless sheet, it's tugging on a quantum network with built-in flexibility and resistance. String theory offers another angle. If the universe's fundamental building blocks are tiny, vibrating strings, their interactions in the quantum foam could manifest as both particles and gravity waves. Think of a symphony where violins and cellos play different notes but harmonize through shared vibrations. Similarly, strings vibrating in foam's hidden dimensions might produce what we observe as gravity on cosmic scales, while their high-energy oscillations create particles at quantum scales. The foam becomes the conductor, ensuring both sections of the orchestra stay in sync. Skeptics argue that without experimental proof, these ideas remain elegant speculation. But subtle clues exist. Some models predict that if spacetime is foamy, ultra-high-energy cosmic rays should scatter slightly as they travel across the universe, an effect that might already be hidden in existing data. Others suggest that future gravitational wave detectors could spot Planck-scale jitters in the signals from colliding black holes, like hearing static in a recording of a distant explosion. Even if direct detection remains elusive, the foam's mathematical consistency across competing theories hints that we're circling something profound. The stakes couldn't be higher. If quantum foam truly bridges relativity and quantum mechanics, it wouldn't just solve equations, it would redefine our understanding of reality's fabric. Time, space, and matter might all emerge from deeper, foam-like processes, like shadows cast by a flickering fire. We'd no longer live in a universe with separate rules for the big and the small, but in a seamless cosmos where every scale whispers the same turbulent, beautiful secret. Time might not flow like a river. It could tick like a stopwatch, with each tick being an indivisible moment called a chronon. This is the heart of the chronon hypothesis, a radical idea suggesting that time itself is pixelated, just like space appears to be in quantum foam. If spacetime is a frothy, fluctuating sea at the Planck scale, then chronons could be the individual bubbles in that foam, tiny, discrete packets of time that can't be divided further. Think of it like flipping through a flipbook. From a distance, the motion looks smooth, but up close, you see it's made of distinct frames. Chronons would be the universe's frames, the smallest possible increments of time stitching reality together. What makes this idea so compelling is how neatly it solves one of physics' lingering paradoxes: the bizarre disconnect between time in quantum mechanics and general relativity. In quantum theory, time is treated as an external backdrop, an unchanging stage where particles dance. But in relativity, time is dynamic, stretching and warping with gravity. Chronons bridge this gap by proposing that time isn't just flexible, it's built from something. Picture a stretchy rubber sheet made of tiny, interlocking beads. The sheet can bend and twist, but the beads themselves remain the smallest possible units. Similarly, chronons could allow time to stretch or compress in relativity while maintaining quantum mechanics' discrete, step-by-step nature. The math behind chronons is as elegant as it is strange. If time truly comes in these indivisible chunks, then there's a limit to how finely we can slice it, no moment shorter than approximately 10 to the power of negative 43 seconds, the Planck time. This isn't just a theoretical curiosity, it has real consequences. For instance, at the chronon scale, the very idea of now becomes fuzzy. Events couldn't happen with infinite precision. They'd have to align with these discrete ticks, like a cosmic metronome keeping the rhythm of reality. Even causality, the unbreakable rule that cause must precede effect, might take on a new texture, with chronons acting like the gears in a universal clockwork, ensuring no effect ever slips out of sequence. But how does this tie back to quantum foam? If spacetime is foamy at the smallest scales, then chronons could be the foam's temporal dimension, the when to go with the where. Each bubble in the foam wouldn't just represent a jitter in space, but a flicker in time, a momentary fluctuation where the universe's clock advances by one tick. Some theories even suggest that the foam's chaotic appearance is a result of chronons popping in and out of alignment, like a film reel with occasional skipped frames. This could explain why time seems to flow smoothly at our scale. Just as a spinning wheel looks solid until you slow it down, the chronon ticks blur into continuity for anything larger than the quantum realm. The implications are staggering. If chronons exist, our entire understanding of time, from aging to black holes to the Big Bang, might need rewriting. Black hole singularities, for example, wouldn't just be places where space breaks down, but where time's granularity is laid bare. The universe's earliest moments wouldn't be a smooth expansion, but a staccato burst of chronons, each tick marking a leap forward in cosmic evolution. Even our perception of time's flow could be an illusion, a side effect of consciousness stitching together these discrete moments into a coherent narrative. So how do we prove it? Direct detection is nearly impossible with current tech. Imagine trying to observe a single frame in a flipbook flipping at 1 trillion frames per second. But indirect clues might lie in ultra-precise atomic clocks or high-energy particle collisions, where deviations from continuous time could leave faint fingerprints. Some models even predict that if chronons are real, light from distant quasars might arrive with barely perceptible timing gaps, like a radio signal flickering as it passes through static. Future quantum gravity experiments could finally catch these whispers from the foam, revealing whether time is truly a tapestry or a ticking clock we've yet to fully hear. Neutrinos are the universe's ultimate ghost particles, nearly massless, barely interacting, slipping through planets like they're not even there. But these elusive particles have a strange habit of shape-shifting as they travel, morphing between 3 distinct flavors: electron, muon, and tau neutrinos. For decades, physicists have grappled with why. The leading explanation, neutrino oscillations, relies on quantum mechanics. But what if there's another player in the game? Recent theories suggest that spacetime's turbulent quantum foam might be nudging these particles, subtly altering their identities as they zigzag through the froth. At first glance, the idea seems outlandish. Neutrinos are famously aloof, rarely bumping into anything. Yet quantum foam isn't just anything, it's the fabric of reality itself, a seething undercurrent that could interact with particles in ways our standard models don't account for. Think of a hiker traversing rough terrain. On smooth ground, their path is steady, but throw in rocks and roots and their gait starts to wobble unpredictably. Similarly, as neutrinos voyage through spacetime, the foam's Planck scale fluctuations might introduce tiny perturbations, warping their quantum states just enough to trigger flavor changes. It's not that the foam collides with neutrinos, it's more like the particles are surfing a turbulent quantum sea, where every ripple tweaks their properties. The math behind this is as elegant as it is speculative. Quantum foam's chaotic structure could introduce minuscule deviations in the neutrinos' phase relationships, the delicate quantum interference patterns that govern their oscillations. Normally, these shifts are calculated in a perfect vacuum, but if spacetime is fundamentally frothy, the rules change. Imagine trying to play a piano concerto in a concert hall where the floor subtly vibrates. Even if the vibrations are imperceptible, they'll distort the music. For neutrinos, the music is their quantum wave function, and the foam's tremors might be enough to alter the tune. What makes this hypothesis so enticing is its potential to explain anomalies. Neutrino detectors like IceCube and Super Kamiok and have recorded slight discrepancies in oscillation patterns, deviations that don't quite fit the standard model's predictions. Could these be whispers of quantum foam's influence? Some models suggest that if foam interactions are real, they'd leave a statistical fingerprint, a telltale energy dependence where higher energy neutrinos, which probe smaller spacetime scales, show more pronounced flavor shifts. It's like noticing that hikers on rougher trails stumble more often, a clue that the terrain itself is shaping their movement. Critics argue that quantum foam's effects would be vanishingly small, dwarfed by conventional oscillation mechanics. But supporters counter that even tiny perturbations could accumulate over cosmic distances. Neutrinos from distant supernova or active galactic nuclei travel billions of light years, plenty of time for foam's whispers to stack up into measurable differences. It's the universe's ultimate butterfly effect, Planck-scale tremors rippling into detectable changes across intergalactic space. The stakes are higher than just solving a neutrino puzzle. If quantum foam affects neutrinos, it's a direct window into spacetime's microscopic structure, a way to test quantum gravity theories without needing a particle collider the size of a galaxy. Future neutrino observatories, like the Deep Underground Neutrino Experiment (DUNE), could hunt for these foam-induced anomalies with unprecedented precision. A confirmed link would mean that neutrinos aren't just passive travelers but cosmic messengers, encoding secrets of the quantum fabric in their ever-shifting identities. Ultimately, this isn't just about ghostly particles, it's about whether the universe's smallest wrinkles leave marks on its most elusive inhabitants. If they do, every neutrino detection becomes a snapshot of spacetime's hidden chaos, a fleeting glimpse into the foam beneath our feet. Einstein would have been stunned to discover that his two most famous ideas, wormholes and quantum entanglement, might be two sides of the same cosmic coin. This is the heart of the ER=EPR conjecture, a revolutionary theory suggesting that black holes connected by wormholes, Einstein-Rosen bridges, could actually be the same phenomenon as particles linked through quantum entanglement, Einstein-Podolsky-Rosen correlations. And hidden beneath this wild possibility lies quantum foam, the chaotic substrate of spacetime that might be weaving these seemingly disconnected concepts into a single, breathtaking tapestry of reality. Picture two black holes born from the same collapsing star, or better yet, two black holes entangled through some prior interaction. According to the ER=EPR proposal, these black holes wouldn't just share quantum information, they'd literally be stitched together by a Planck-scale wormhole threading through the quantum foam. It's like taking two corks floating on an ocean and realizing they're actually connected by a hidden rope beneath the waves. Except in this case, the rope is a spacetime tunnel so warped by the foam's turbulence that it defies classical notions of distance. The brilliance of this idea is how elegantly it bridges relativity and quantum mechanics. In Einstein's general relativity, wormholes are hypothetical tunnels through spacetime's fabric, shortcuts between distant points. In quantum theory, entanglement creates instantaneous correlations that seem to ignore space entirely. ER=EPR suggests these aren't separate phenomena but different descriptions of the same underlying structure, a structure built from quantum foam's churning, probabilistic foundation. Imagine shaking two ends of a tangled phone cord. From one perspective, the jiggles look like separate events but pull the cord taut, and you see they're part of a single, continuous thread. Similarly, entangled black holes might appear separate until you account for the foam's hidden geometry, revealing their secret connection. What makes quantum foam crucial here is its role as the ultimate mediator. At the Planck scale, spacetime isn't smooth. It's a frothy, dynamic mess where wormholes could constantly form and vanish like bubbles in boiling water. The conjecture proposes that some of these fleeting tunnels stabilize when systems become entangled, creating a durable, though still microscopic bridge. It's as if the foam's chaotic fluctuations occasionally freeze into a pattern that links distant points, providing a physical substrate for what we observe as entanglement. This isn't just theoretical poetry, it has concrete implications for how black holes handle information. The infamous firewall paradox, where an observer falling into a black hole encounters a wall of searing radiation, could dissolve if the black hole's interior connects to another region via a foam-forged wormhole. Information wouldn't be lost, it'd be rerouted like data flowing through a hidden backup cable. Even Hawking radiation, the faint glow black holes emit, might carry encrypted messages about the foam's structure, as if the wormhole's geometry imprints itself on the escaping particles. Skeptics argue that ER=EPR remains untested, and they're right for now. But upcoming gravitational wave detectors could hunt for subtle signatures, like paired black holes whose mergers leave anomalous echoes, hinting at unseen wormhole connections. Others suggest that high-energy particle collisions might momentarily create entangled micro-black holes, offering a lab-scale glimpse of the foam's spacetime stitching in action. The most profound takeaway: if ER equals EPR holds, it means the universe's spookiest phenomena, entanglement, wormholes, even black holes, are all manifestations of quantum foam's hidden architecture. What we call spooky action at a distance might just be spacetime's way of reminding us that beneath the illusion of separation, everything is fundamentally, intimately linked. In the bizarre world of quantum mechanics, particles can exist in multiple states at once: an electron spinning both clockwise and counterclockwise, a photon traveling two paths simultaneously. This ghostly behavior, called superposition, vanishes the moment we try to measure it, collapsing into a single, definite state. Physicists call this process decoherence, and for decades they've blamed it on interactions with the environment. But what if something more fundamental is at work? Enter quantum foam, spacetime's own turbulence, which might be quietly erasing quantum weirdness at the smallest scales. Think of a perfectly still pond reflecting the moon's image with crystal clarity. That's a quantum system in superposition, pristine, unobserved. Now toss a handful of pebbles into the water. Ripple after ripple scrambles the reflection until only fragmented light remains. Quantum foam could be those pebbles, constantly disturbing spacetime at the Planck scale. Even in a perfect vacuum, shielded from all environmental noise, the foam's relentless fluctuations would jostle any quantum system, disrupting delicate superpositions like static overwhelming a faint radio signal. Unlike traditional decoherence, which requires particles to bump into atoms or photons, foam-induced collapse would be inescapable, written into the fabric of reality itself. This idea turns conventional wisdom on its head. Most decoherence models treat spacetime as a passive stage, but if it's actively frothing, its turbulence becomes an unavoidable measuring device. Imagine trying to balance a pencil on its tip in the middle of an earthquake. No matter how carefully you position it, the ground's tremors will knock it over. Similarly, quantum foam's fluctuations might continuously measure particles, forcing them to pick a state long before any human observer intervenes. Some calculations suggest this could happen astonishingly fast, superpositions of large objects lasting mere fractions of a second before foam-driven decoherence crumples them into classical certainty. The implications ripple across physics. For one, it could explain why we never see cats both dead and alive. Macroscopic objects are simply too big to withstand spacetime's microscopic chaos. Their countless particles interact with the foam's frenzy at slightly different rates, multiplying decoherence effects until quantum weirdness drowns in the noise. It's like 1,000 pebbles hitting that pond at once. The reflection doesn't just blur, it vanishes entirely. This might also solve the measurement problem's thorniest aspect: why observation collapses the wave function. The answer: it doesn't. Quantum foam is always observing, always measuring, its Planck-scale churn acting as nature's ultimate referee. Critics counter that foam-induced decoherence lacks experimental proof, and they're right for now. Yet subtle hints exist. Some interpretations of high-precision quantum experiments show particles decohering faster than environmental interactions alone can explain, as if an unseen hand is nudging them toward classicality. Others point to anomalies in light traveling from distant quasars, whose quantum states might bear scars from foam's cumulative disruptions across billions of light years. Future experiments with even more isolated quantum systems, perhaps atoms suspended in ultra-cold traps or particles orbiting Earth in vacuum-sealed satellites, could tease apart foam's role from other decoherent sources. What's at stake isn't just another mechanism for quantum collapse, but a radical rethinking of reality's boundaries. If quantum foam drives decoherence, then the line between quantum and classical isn't drawn by observers or technology, but by spacetime's own restless energy. The universe wouldn't just contain quantum laws, it would enforce them, its very structure acting as a cosmic sensor, smoothing the wild quantum realm into the familiar world we know. In this view, the foam isn't mere background noise. It's the loom weaving possibility into actuality, one Planck-sized tremor at a time. Imagine tapping into an energy source so vast it could power civilizations for eternity, an infinite wellspring hidden in the very fabric of space. This isn't science fiction, it's the staggering promise of zero-point energy, the quantum foam's restless hum of particles appearing and vanishing in the void. According to quantum field theory, even in a perfect vacuum, spacetime isn't empty but thrums with activity, a seething ocean of virtual particles borrowing energy from the universe before disappearing again. If you could somehow harvest even a fraction of this energy, you'd unlock a power source beyond anything we've ever known. Here's the catch: while the math suggests zero-point energy is infinite, actually extracting it is like trying to bottle lightning. Quantum foam's fluctuations exist at scales so small and fleeting that they defy conventional engineering. Think of it like standing beside a raging river with only a teaspoon. The water is everywhere, but capturing meaningful amounts feels impossible. Yet physicists and futurists aren't ready to dismiss the idea. Some theories propose that advanced technology, perhaps nanotechnology or exotic materials, could one day smooth out pockets of foam, stabilizing its energy for use. It's the cosmic equivalent of calming a stormy sea just long enough to skim energy from its waves. The implications are mind-bending. Zero-point energy could revolutionize space travel by providing propulsion without fuel. Imagine spacecraft riding the quantum foam's ripples like surfers catching an endless wave. Theoretical designs like the Alcubierre warp drive, which bends spacetime to achieve faster-than-light travel, rely on harnessing this very energy. Even closer to home, zero-point devices might offer clean, limitless power, rendering fossil fuels obsolete. Picture cities lit by quantum vacuum batteries or medical nanobots drawing energy from the fabric of space itself. But the challenges are just as monumental. Quantum foam's energy is chaotic, and tapping into it risks triggering catastrophic feedback loops, like poking a hole in a dam holding back an ocean. Some calculations suggest that extracting zero-point energy on a large scale could destabilize spacetime, creating artificial singularities or even unwittingly rewriting the vacuum's fundamental properties. It's a cosmic version of the Sorcerer's Apprentice. We might unleash forces we can't control. That hasn't stopped researchers from exploring creative workarounds. One approach, inspired by the Casimir effect, involves using microscopic plates to manipulate vacuum fluctuations, effectively pressing energy out of the foam. Another wild idea involves quantum dots, engineered nanostructures that resonate with zero-point fluctuations, acting like tuning forks for spacetime's hidden vibrations. Even if these experiments only yield microscopic amounts of energy, they could prove the principle, opening the door to scaling up. The zero-point energy connection forces us to confront a profound question. Is the universe's vacuum a silent, passive backdrop, or an untapped powerhouse waiting to be understood? For now, the foam's energy remains locked away, a tantalizing what-if at the edge of physics. But if history has taught us anything, it's that today's impossible often becomes tomorrow's breakthrough. The quantum foam's infinite whisper might just be the future's loudest revolution. What if our universe is just one bubble in an endless cosmic froth? A single note in a symphony of realities, each humming with its own unique laws of physics. This exhilarating possibility emerges when quantum foam meets multiverse theory, suggesting that spacetime's turbulent foundation doesn't just shape our reality but endlessly births new ones. Picture a pot of water on the verge of boiling, where tiny bubbles form, rise, and detach into the steam. Now imagine those bubbles aren't made of water but entire universes, each pinched off from the quantum foam with its own random set of physical constants. Some might inflate into vast cosmos like ours, while others collapse instantly or stabilize into bizarre realms where gravity is repulsive or light moves at a crawl. The math behind this is as breathtaking as the imagery. Quantum foam's fluctuations aren't just random noise, they're spacetime's way of exploring every possible configuration, a process called vacuum decay. In this view, our universe began when one such fluctuation tunneled through an energy barrier, creating a bubble of false vacuum that rapidly expanded. But here's the twist: the same process could be happening eternally in the foam's churning depths, with new bubbles nucleating endlessly. Think of it like a tree growing apples. Most seeds fall where they can't sprout, but a few land in fertile soil. Similarly, most quantum bubbles might vanish instantly, but a rare few find the right conditions to inflate into full-fledged universes. This isn't just theoretical poetry. The idea, known as eternal inflation, solves one of cosmology's deepest puzzles: why our universe seems fine-tuned for life. If countless bubbles arise with random physical constants, statistically, a handful will inevitably land on the right numbers for stars, planets, and conscious observers. It's the ultimate cosmic lottery. We're here because our bubble won the jackpot, and the quantum foam. It's the machine printing those lottery tickets. It's restless energy fueling the creation of realities beyond counting. Some bubbles might even brush against ours. Certain models suggest that when newborn universes pinch off from the foam, they could leave faint gravitational imprints on their neighbors', cosmic bruises in the cosmic microwave background, or odd voids in galaxy distributions. Others propose that bubble collisions might create singular, explosive events detectable as anomalous radiation bursts. It's like living in an apartment building where you occasionally hear the neighbor's music through the walls, except the walls are spacetime itself, and the music is the birth cry of another universe. Critics argue that without observable proof, this remains speculative, but supporters counter that the multiverse's invisibility might be a feature, not a bug. If bubbles nucleate in regions of spacetime causally disconnected from ours, no signal could ever reach us. That doesn't mean they're not there, just that the foam's creativity is hidden by the sheer scale of its productions. Future advances in quantum gravity or high-energy physics might uncover indirect hints, like statistical anomalies in particle behavior that point to foam-driven leaks between realities. The most humbling implication: quantum foam could be the ultimate cosmic recycler, endlessly spinning up new worlds from its flickering energy. Our universe, with all its grandeur, might be just one ephemeral bubble in an infinite foam, a temporary pattern in spacetime's endless dance. It's a vision that collapses the distinction between creation and destruction, where every vanishing fluctuation might seed another Big Bang, and every black hole's death rattle could whisper the birth of something new. From bubbling wormholes to cosmic holograms, the wild frontier of quantum foam has taken us on a journey through 25 theories that shatter everything we thought we knew about reality. We've seen how spacetime's turbulent undercurrent could hide miniature tunnels connecting distant points, how its seething energy might fuel the universe's accelerating expansion, and even how it could silently encode information like a cosmic hard drive. The holographic principle suggests our entire three-dimensional world might just be a projection on spacetime's two-dimensional surface, while theories like ER=EPR propose that black holes and entangled particles are secretly stitched together by the foam's hidden threads. Time itself might not flow smoothly but tick in discrete chronons, and the vacuum's infinite zero-point energy could one day power civilizations. What makes these ideas so transformative isn't just their strangeness, it's how they force us to rethink the very fabric of existence. Quantum foam doesn't just tweak the rules, it rewrites them, revealing a universe where space and time are neither smooth nor absolute but dynamic, granular, and alive with possibility. Whether it's loop quantum gravity spin foam weaving spacetime from discrete loops or the simulation hypothesis suggesting reality is rendered at the Planck scale, one thing is clear. The closer we look, the less the universe resembles the orderly, predictable stage we once imagined. Yet for all we've explored, this is just the beginning. Every theory we've touched on, from foam-driven dark energy to consciousness emerging from spacetime's turbulence, opens new questions. Could future experiments catch whispers of foam in neutrino oscillations or gravitational waves? Will we someday harness zero-point energy or even glimpse other bubble universes in the cosmic background? The answers are still out there, waiting in the quantum chaos. Now it's your turn. Which of these theories bends your mind the most? Is it the idea that black holes might be gateways, not graves? Or that the universe could be a hologram projected from its edges? Drop your favorite in the comments. We're all navigating these mysteries together. And if you're hungry for more deep dives into the cosmos's weirdest corners, don't forget to subscribe. The universe has plenty of secrets left, and we're just getting started.